This is Project 22050, the MicroDx platelet-derived microparticle detection system. Here is our project poster, which we will go into more detail over the course of this presentation.
Heart disease is the leading cause of death in the US, with 659,000 deaths every year. This only accounts for deaths per year and not for the amount of patients that live with heart disease. Most of these patients require treatment using blood-contacting medical devices, including stents, replacement heart valves, and catheters. Many of these devices are effective and life-saving, but all come with the risk of blood clotting, which is in part caused by the up to 100-fold increase in shear forces from these devices. These immense shear forces can activate and shred platelets, which are cells of the blood that are responsible for blood clotting. The shredding of platelets creates platelet-derived microparticles, or PDMPs, which brings us to the focus of our project. Research has shown that there is a relationship between PDMP formation and increased thrombosis. Thrombosis referring to blockage of veins and arteries due to blood clots. Being able to detect and size these PDMPs, which range in diameter from 100 to 1,000 nanometers, will be very helpful in understanding and managing cardiovascular disease.
The project has been broken down into three main phases of testing, the first of which marks the project's current status. In the preliminary and current phase, the system was tested using polystyrene microsphere samples of a single particle size. In the intermediate phase, the system will be tested using polystyrene microsphere samples of multiple particle sizes. In the final phase, the system will be tested using real patient blood samples. The team will deliver a low-cost system with point-of-care capabilities that can measure the diameter of polystyrene microspheres from a sample of single-sized particles within the range of 500 to 1,000 nanometers. This senior design project is the first attempt at creating a platelet-derived microparticle detection system, so we started off by researching methods of detection. Dr. Slepian provided several research articles for us to consider at the launch of our project, and we reached out to several faculty members from the Wyatt College of Optical Sciences. The team initially chose to move forward with the method of laser diffraction, but after we began testing our prototype in January, we quickly realized that this technique would not work for our system. We eventually were connected with Dr. McLeod, and he suggested using the method of dynamic light scattering, which is a technique that has been used to measure nanometer-sized particles in other applications. Since February, we have put in long hours in the optical lab space to collect data for our project, and we have been able to develop a system with this technique. Our initial prototype utilized a large amount of equipment that was borrowed from the optical lab space, but since then we have substituted the borrowed parts with parts of our own, and we have 3D printed an enclosure for our system to rest in.
In our sponsor's lab, our team made a number of dilutions of synthetic microparticles in DI water so we can test various concentrations. To test our samples, first we shook the vials to make sure that the particles were suspended. Then we pipetted each vial into a cuvette and placed it into the system.
The overall system design is made up of a 520 nanometer compact laser module that shines through a plano convex lens with a focal point of 5 centimeters and then passes through an unfrosted cuvette containing a microparticle sample. The lens ensures that the light rays meet at the center of the cuvette to reduce the size of the beam before finally reaching the avalanche photodiode. That reads the varying changes of light intensity over time with the help of an oscilloscope. The four main optical components are held within a rigid assembly using 3 optical posts and pedestal holders, lens and kinematic mounts, and a 3D printed cuvette holder fixed with through holes and a pedestal to provide the ability to accurately adjust the system to the necessary distance and height requirements. These parts are then bound to an aluminum breadboard with cap screws that can be adjusted if movement within the system has occurred. This full assembly is then placed inside of an enclosure and closed off with a system access wall that has been 3D printed using PLA and painted inside and out with matte black to ensure that outside light and reflections do not affect the performance of tests.
The sample scatters light, forming a speckle pattern. Dynamic light scattering reads the intensity of the speckle pattern over time and runs the data through an autocorrelation function, which produces a graph that we average over many data samples to get more accurate results. Then a function that fits the curve is calculated, and its coefficients are used to calculate the hydrodynamic size of the particles using the Stokes-Einstein equation. Smaller particles will become uncorrelated faster, while larger particles will become uncorrelated more slowly.
Our verification tests were separated into 3 main areas, being our optical, data file, and software tests. For For optics, we were ensuring that the system could output the correct sizes for 3 samples within 50 nanometers. For data files, the system needed to create, save, and export files for users. The software needed to be able to use the autocorrelation function in order to calculate the particle sizes within 50 nanometers. We also had a set of inspections for the design, ensuring that the system was proper for a clinical setting, that it was safe to use, and that the GUI could properly display results.
We have verified the inspection and data file requirements of the MicroDx system, and have also tested our optical and software components by collecting size data for 500, 720, and 1000 nanometer samples. We observed that many data points severely overestimated the particle size, which may have been caused by larger particles in the air. Since the rest of the results were pretty consistent, we removed such outliers, which increased our accuracy. We also noticed that the removal of extremely variable segments of the autocorrelation plots improved the accuracy of our calibration curves and our size calculations. Ultimately, our results for the 720 and 1000 nanometer samples were mostly within the plus or minus 50 nanometer buckets, whereas the 500 nanometer results were more variable. We have proposed ideas for the concentration and mixed particle functionalities and have attempted a few sets of experimental data collection for the mixed particle sizes. Our results for these tests varied greatly, and significant improvements will need to be made for the completion of these future phases.
To ensure that safety and environmental standards have been met, we have integrated a completely closed-off enclosure so that laser light does not damage the user or anyone surrounding the system. To take this further, the user is able to power the laser on and off from the GUI before entering the system and replacing the sample. In terms of electrical safety, all wires have been grouted and fed through a hole within the enclosure and set within the box below the GUI. With all electrical and mechanical standards met, the user is required to have the proper training in handling microparticles and blood to reduce extraneous risks.
The team overcame a number of obstacles in this project, mainly stemming from not having an optical engineer. Because of this, we began working with Michael Skur, an optics graduate student who helped us implement the laser diffraction technique in our design. Unfortunately, Michael was unable to continue supporting the project after the fall semester due to a family emergency. The next big obstacle was getting lab space. Initially, the optics department denied us a space, but thankfully, Dr. Koschel, the associate dean of the optics department, granted us access, and we began working a few weeks into the spring semester. However, the largest challenge the team faced was moving from light diffraction to dynamic light scattering. This required us to use new equipment, new methods for acquiring and analyzing data, as well as new procedures. This resulted in the team working early mornings and late nights in order to get the verification data needed for the system. Each of these challenges has shown the dedication of the team and our diligence in completing the project.
Our deliverables for this project include the physical MicroDx system, complete with the system manual, software and computer component specifications, and the experimental data analysis sheets. Other deliverables include the technical data package and final report, a complete list of all fabricated equipment, a cost analysis of purchased and fabricated equipment, and our finalized drawings. Our sponsor, Dr. Slepian, also requested that our team submit a proposal and abstract for this year's ASIO competition and begin preparing an academic journal entry.
This concludes our video. Thank you for watching and listening. We would like to thank all of the following for their guidance and assistance, including our sponsors, our mentor, and everyone else that helped us along the way.